Hi, welcome back to another episode of Polly's Introduction to Computer Networks. All right, so the announcements, just like all the Thursdays, there's nothing more to say. Okay, we've talked about all the new stuff yesterday. Maybe the only thing that's slightly new is that this link we've been using for call-ins, that will also be the link for the test run. Okay, later today. So this is a test for you to check whether your camera and internet connectivity will be okay for the exam next week. All right, let's go ahead and check out the topics today. You know what? Yesterday, Polly has overview. The last topic about HTTP and web browsing are the caches. Okay, and there are two kinds of cache. The first one is local cache. This is the simple form. This video, about 3 minutes, local cache. The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. So what cache means is to store a temporary copy of certain data. Okay. So conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay. So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay. Because as a result, we don't need to send the object, and that reduces the delay, and we also reduce the bandwidth requirement. Okay. And so saving the bandwidth is going to be good for everybody. So the way it works is this. So the first time the client downloads a web page, it's going to keep the copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modify since, and then the date, okay, of the cached copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cache copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, okay, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. Yeah, 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modify since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T. Yeah, so you see, using this special header line, if modify since, right? The client can check whether the web object has been updated. If not, then the server doesn't need to send the object again. Why waste the bandwidth to send the same thing again? Okay, so that's a local cache. It's to store the web object temporarily on the local hard drive. Okay. The second form of caching, web cache, is actually to store this copy of web object in the middle, okay, between the client and the server. And we call that machine a proxy server. This video, about 3.5 minutes, explains the mechanism of the proxy server and how it works. Web caches. The purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. Okay. The main difference is this. In local caching, we keep a copy of the object here. Okay. But now we keep a copy of the object here in the web cache, also known as the proxy server. Web cache or proxy server. Okay. And in conditional get, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay, sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client request such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the object somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay. So object in the cache, cache return objects. Otherwise, the cache here, the web cache here, would request from the server a copy of the object. So this request will be like, the proxy server here behaving like a client of the original server. Web cache there, request object from the original server like a client. Okay. And after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, request go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there acts both like a client and a server. As a server, so that it serves the original client, the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So, some of you might see already, right? A web cache like that is actually preferred by the ISPs, okay, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. Okay? So a lot of times ISPs might encourage you to set a web cache on your browser. Now let's go through a few examples to detail why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of example, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving.
Yeah, so in the next 3 videos, Polly will show you an example. And with scenarios one on top of another, you will see the benefit of doing web caching. Now, we see also on the chat that Miguel, Justin, and Sylvain are asking questions about these caches. They are a lot more security or consistency aware. Okay, guys, I'll come back to answer these questions after we are done with caching. Okay, so you guys' concerns are all valid because caches are temporary. Caches are also stored somewhere that might be easy for people you don't trust to tamper. Indeed. Okay, or the system to crash so that there is inconsistency. Okay, so let's go through all the mechanisms first, and then we'll come back to discuss these. So the 3 scenarios. This is the example with the base scenario.
Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, coming down this way. Right? And that is 1.5 megabits per second. Now, let's see. round-trip delay from the institutional router to any of the origin servers and back. That's set up to 2 seconds. And the access links rate 1.54 megabits per second. And the local area network link rate 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hop, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. But as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right? So close to 1, close to 100% delay, just very long. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here, plus round-trip delay here, plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay, now this is very low because utilization is super low. So let's say microseconds, right? So 3 components, which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here, in terms of delay performance. How do we fix this? Let's look at the second scenario.
Yeah, so you see in this first scenario, with the bottleneck link, the delay can go up high as in minutes. Okay, so how do you fix this? You're seeing the second scenario. How about we expand the bandwidth of that bottleneck link? Okay, Sophia. Okay, so I'm gonna tune up the volume a little bit more, and the rest of the class, in case it's too loud, you wanna also lower the volume from your end. Okay, I guess Sophia might be using specific devices that there's a maximum of the volume. Yeah, Sophia, just let me know, okay, if the volume is a little bit better. So I just tuned the volume up by like 1/4. Hope that it's good enough. If it's still low, just let me know. Okay. So the second scenario, this one is straightforward. We just expand the bandwidth of the bottleneck link.
In scenario 2, let's try to address the issue here, because this is the bottleneck link where the delay came from mostly. And let's blow it up 100 times. How about that? So using a fatter access link there. The result is that the access link utilization is also reduced 100 times. Less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between 2 routers are what? Tens milliseconds and maybe 100 milliseconds at most. So if there's not going to be much queuing delay, yeah, the delay is at this scale. So 2 seconds, milliseconds, microseconds, which of these 3 components dominates? Obviously, 2. And from scenario 1, we have minutes of delay, to scenario 2, we effectively bring down the total delay. All right, great. Is there any catch? if you think about it, hey, bringing the access link capacity up 100%, that is actually not cheap. So increasing access link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link.
Okay, so you see here, expand the bottleneck link, then you take that delay component, that time from minutes down to seconds. Okay, very straightforward change, but the cost is very high. And in scenario 3, which is quite long, it's probably one of the longest videos in the whole semester, 7.5 minutes, you will see installing a web cache or the proxy server locally give you the same benefit without the cost of expanding that bottleneck link.
In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. All right. So we are only slightly local here, so to speak. Good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the two routers. For your information, this could take millions of New Taiwan dollars. But installing a high-end server machines, it only takes this much New Taiwan dollars. So that's about 2 order of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, all right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the clients without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the requests being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the access link, 60% of the scenario 1. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, And then web cache serve the local client. We have one copy done here and another copy done this way. So the length here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, say tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content, all right? And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Okay. And you saw a bit already. Next slide. Coming next is going to be the second application in chapter 2. And we'll look at how FTP defines its application layer protocol.
Yeah. So the next topic Polly has planned is FTP. But we'll skip this topic as it is not described in the textbook. And in the interest of time, we'll actually skip to the next topic called email. This is the second application we'll talk about. Okay. But before that, let me come back to address the 3 questions about caching. Let me start from the easier one. So Sylvain asked, does web caching also work with HTTPS? So HTTPS is the secure version of HTTP. So HTTP is to send web objects over a TCP connection. HTTPS is to send web objects over a secure TCP connection, a TLS connection. Okay. Sylvain, the connection is secure. Okay, so content before entering the transport connection, it's encrypted. So it's secure in the transport connection. But after it arrives at the other end, it will be decrypted. So in the cache, the content will be decrypted, open to everyone. Okay, so web caching is something that's general independent of the transport layer or the application layer connection that you're using. Okay, so if the original web object is open not encrypted, in the cache it's open not encrypted. Okay, and whether you cache the object when you receive it here or at the proxy server, it depends on the configuration, and they will work independent of each other. Okay, I hope that answered your question. Second and the third, Miguel and Justin are asking about consistency or whether you can verify, right, the object is still fresh enough. Otherwise, you might be reading the old data, okay, although you save bandwidth. And I guess particularly we don't like to keep sending, right? If modify since request and wait for a response, even though the objects are not set, maybe we can save that exchange entirely. If the local cache or the proxy server can somehow verify the freshness or consistency of the cache, okay, in the background, without the users knowing. You know what? That is something that the web proxies, some of the web proxies implementation have tried to do. So they do periodic check, okay, in the background on a regular basis. Some research, okay, also indicate that if you profile the request patterns of these objects being cached and you you refresh these objects according to the pattern, it would also make it more bandwidth efficient, okay, and in the meantime increase the hit rate. So in a web proxy server, this can be done easy, as that proxy you kind of need to run the server and the client at the same time. It's a specialized software, so adding this consistent checking or periodic refreshing mechanism is not an issue. But Miguel, for local cache, so local cache is maintained by the browser. So regular web browsers do not do this. Okay, this might be a lot of work in addition, and it will consume your background bandwidth. And as a local user, this is considered something that's extra, and you might want to conserve. Okay, so local cache, I rarely see that there's verification software on top of the web browser to do this. Okay. Good, I hope that I answered all the questions, and now we can move on to the second application, email. Okay, so when we talk about the second application, you will see how we use email. Okay, we know the application, but there are some application layer protocols defined and implemented to support this application. Okay, and you will see in this particular application, there's not just one. We just talked about HTTP. It's the application layer protocol for web browsing. One protocol for web browsing. But for email, you will see there are many of them. In fact, in this video coming, you will see the components involved, okay, to support this application called email, and how they are structured, and the kind of sockets we open to send emails around. Okay, so it's very different from HTTP web browsing. Okay, so this video is 5 minutes long, a little bit long, but it talks about the basics of email.
2.3, emails. So this application is a little bit unusual. It's supported by not only one application layer protocol, but multiple ones. And we'll talk about it more. Email application. It's got three major components. First is the user agent. This is the software running on the machine closer to the users. And mail servers are the software running on more resourceful machines farther away from the users. And among these mail servers, it runs this protocol, SMTP, the Simple Mail Transfer Protocol. These we'll also talk a bit more about that start from the user agent. They're essentially the email readers. They allow us to write email, edit email, read emails. Outlook from Microsoft is one mail reader that's very well known. Thunderbird, I don't know if you know about this one. This is from Mozilla. So the company that produces also Firefox, the very well-known web browser. iPhone comes with a built-in mail reader. Google is also trying to push for a Gmail mail reader. So there are so many of these email readers these days. Now, keep in mind though, the actual emails are all stored on the servers, not on the user agent these days. All right. Now the mail servers. It's got these three major components. The mailbox, which contains all the incoming messages per user. So these are the yellow boxes. When emails come in, they will be sorted out and then put into the email boxes depending on who the receivers are. Second component, the message queue. Those are the green queue over here. So messages that are going out will all be stored here temporarily and waiting for the receiving mail server to open up and then accepting the emails. So SMTP protocol there is to allow the sending server and the receiving server to communicate. Now here in particular, the sending server there is called the client of the SMTP protocol, and the receiving server is, on the other hand, the server of the SMTP protocol. So you see a little bit here, the SMTP protocol is to provide mail receiving service in a sense. So client here requesting service, server here allowing emails to come in. If you think about it more, it's got two levels of communications in the email application. So this is one between the end users and the local mail server. Okay, fetching email or pushing email out. But there's another level which is among the mail servers. All right, so sending mail server is the client of the higher level communication. Receiving mail server is the server of the higher level communication. Then the SMTP protocol. So this is the actual application layer protocol defined to support communication in emails. So let's see, what are the underlying protocols and what is the communication model and what are the messages defined? TCP you see here. Therefore, SMTP is to support reliable email receiving service. It runs on port 25 and the transfer is direct between the sending and the receiving server. The exchange, very simplistic, three phases, handshaking, and then extra transferring of the emails, and then closing. Opening, closing, the extra transferring of the emails in between. The messages are also simplistic. They're just comments coming from the sending server, responses coming from the receiving servers. So comments in ASCII code, just like HTTP, just like FTP. Responses, status words, status phrases, status code, just like HTTP and FTP. They all run in the ASCII code. Now put all three major components together and let me illustrate with a concrete scenario. Alice here is sending an email to Bob over there. All right, so Alice will need to start the user agent first to compose an email. So in the email, it will need to specify the receiver. And then the user agent will send the email to the message queue, okay, in the local mail server. So that is step 2, emails going to the message queue. And then the client side of the SMTP, which is here, this guy is the one sending, and this Bob's mail server will be the one receiving. So this is the client of SMTP. This is the server of the SMTP. So client side of SMTP will open up a TC connection. Once the server is allowing the connection, then the client can begin sending Alice's email. So that email will travel, and the server here of Bob's will check whether the receiver is Bob, and therefore putting the email into Bob's mailbox. Right? So email goes to Bob's mailbox. Lastly, when Bob now joins the internet, invoke his user agent, then the agent already pre-configured to connect to the incoming mail server will then fetch the mail messages, and that's when Bob gets to read the email.
Yeah, so you see email, hey, quite different, right, from web browsing. If you think a little bit more, in web browsing, we're users and we ask for information, but those information are provided by some organizations. These informations are well organized structure already and stored in the servers already, waiting for us to ask. Okay, but email is what? We sending information to each other. Okay, user to user, end user to end user. So Where are the servers? And you know what? We as users are moving around. I mean, for you guys, you're attending lectures. Okay, for some other people, they are probably taking the metro, on the run, going to the next lecture. So we're everywhere. Okay, if you send the email to someone like that, where would the email go? Well, the email must go somewhere. Okay, right? The receiver will eventually be able to discover. So those some machines that are allowing the users to access are the mail servers. Okay, and these mail servers, okay, my mail server, your mail servers, will need to communicate to each other, sending emails on my behalf to you, or you receiving the email from that server, or vice versa. So there's a mail server network at the higher level, and between users to their mail servers, there's another level of communication. Okay, so you begin to see elaborated architecture here in this particular application, email. Okay, now let's work on a quiz first before we go on to the details of SMTP, the message formats, the email format. Okay, so this is quiz 12. If you pay attention to the mechanism of email, you will see in the end there's an illustration, okay, an example. So Alice there sends email from the user agent using SMTP protocol to Alice's mail server, okay, which is here, okay, here. And Alice's mail server can send this email to the receiver's mail server. Right? And there's an incoming queue here to store the email temporarily, okay, before Bob come and access it. So in that scenario, you hear Polly saying, well, Bob will eventually come access and fetch the email, okay, like this. Okay, why not? Why not? The server here just somehow push the email to the user agent. Okay, why not it's being pushed directly, for example, using SMTP, just like user agent Alice here push the email to the server. And here, sending mail server pushing to receiving email server. How come we cannot just push, okay, these emails directly to the user agent? Okay, so this is what the question is about. How come we cannot just push the email directly through SMTP to Bob? Okay, now this might be a little bit tricky, guys. Find your teammates. You have 5 minutes to discuss. Okay, and Polly is gonna take the quick solver. So let's go to the score space. Yeah, there's a channel, W5 quiz 12. Gather your teammate and Polly will start counting time. It's 10:59. Oh, wait. Okay, we have quick solvers, but hey, let's be fair. You have 5 minutes, okay? The rest of you, think about it. Think it through. You have 5 minutes, including thinking and typing it up. Guys, by the way, there's no standard answer for this question. So you see, team 2 and 1 are demonstrating what they think makes sense. Okay, let's see. Sophia, I think you are team 3. It's used for sending information, but it's not access protocol. Yeah, okay, Sophia, you knew about the mail access protocol even though we haven't talked about it. Yeah, POP3 and IMAP are mail access protocols, allowing an email reader to access the incoming queue in the mail server. Okay. So this is an answer based on known knowledge. Okay, very good. Okay. So Sylvain, on behalf of Team 2, is saying this. Okay. SMTP obviously is used between servers, or the receiving end needs to be a server, right? Aldous sends through SMTP to Aldous's mail server. Okay, so obviously SMTP here assumes that the server is gonna, the receiving end is gonna be always there. Yeah, this is the key. SMTP is a protocol that assumes that the receiving end is always there. If you recall in the video, Polly said that, hey, there are 2 layers of communication. At the top, there are lots of mail servers. The receiving end is the server of SMTP. So the receiving end of the SMTP exchange needs to be always there. There you go. And so, Sylvain, you have good intuition. So you see that Bob, as a regular user such as us, we are not always online, and we are probably not using a static IP address allowing the sending SMTP servers to always able to reach us. So Bob's computer is off, could be off, right? Yeah, so Bob's user agent might not be reachable, okay, much of the time in a day. Okay, very reasonable justification why the receiver's mail server does not use SMTP to push email directly to the user agent, to Bob's user agent. Bob's user will always have to be exactly, right? Zach also discovered this. In order to receive that email through SMTP, because SMTP assumes the receiving server is the server end of SMTP. So SMTP is expecting the receiving end to be always on. If user agent is the receiving end, it's not a guaranteed thing. Okay, it's not going to work. Okay, for SMTP. Yeah, we need a server in place. Exactly. Okay, Sophia knew that we use mail access protocols. Okay, so obviously we don't use SMTP. Okay, but Sophia, I hope you see that why we don't use SMTP. In fact, the reason we use separate protocols like POP3, IMAP to access email is first because we couldn't just use SMTP to push emails to Bob first. And therefore we need something else, okay, to address this issue, to allow Bob to fetch emails. Yeah, so in a way, Sophia, think this being what we can do after we realize that SMTP is just not the right thing for this part of the whole connection, or the whole pipeline of sending an email. Okay, great. Is used to send data away. Protocol suitable for getting data down from the server. Have to use another protocol. Is not suitable. Okay, good. Very good. SMTP designed for the client. Receive, since the receiving may not be always available. Exactly. We can't guarantee that Bob. Exactly. Okay, I see Kevin is probably hitting the enter accidentally. Good, you guys get it. So a lot of times you see elaborated architecture like this, there's a reason for it. Okay. SMTP is one of the very, very early protocol designed. It actually assumed that the receiving end is always there. Okay. But when it comes to the receiving user who's not always there, then what do? You set up a local server there. You set up a local server who's always there, okay, to receive the emails. So therefore, there needs to be an incoming queue to store these incoming emails until Bob wakes up and try to download using POP3 and IMAP. Okay. So guys, there are usually reasons behind everything we do. If there are no reasons, hey, think again. Think again. It's a bit risky doing things for no reasons. Don't you think so? Yeah, I guess with this discussion here, exercise here, we kind of slow down, then you get to think about the whole system, email system again, okay? It makes it a lot more clear, isn't it? All right. So now let's talk more about SMTP, but the boring side of it, okay? It's the syntax and the messages we send. Towards the end, you will see Polly try to demo accessing a mail server on the internet. And that unfortunately was a failure. And you'll see why.
This is a very simple SMTP exchange. Let me explain the notation. S being the server, C here being the client. Now in SMTP, this is the receiving mail server, and this is the sending mail server. Once the TCP connection is established, the receiving side identifies itself first. 220 hamburger IDU, status code, status phrase. Client here then would in turn tries to identify itself as well. Crepus.friends, that's the identity. And hello here is the command to allow the server to know who the client is. And then server, status code 250, everything is fine. Hello, crepus.friends. And then beginning from here, we start to see control message exchange. Client here needs to specify who the sender is and who the recipient is. So mail sender is Alice and mail recipient is Bob. So all capital here, mail from. All capital here, receive to. Okay, our special commands as well, just like the hello. So whatever comes after the columns are the mailer and the recipient. So server again are just saying, okay, good, I got it, 250. And from here on, this is the actual data exchange. Data, once again, the command. Email starts from here. Do you like ketchup? How about pickles? And it ends with a single line that has only a period. Okay, so the actual email message is only this short, 2 lines. Last is here, just to close. Okay, server will say, message accepted, everything is fine. Client then issue yet another command to quit the session. Server says, all right, goodbye. Very simple. To set up connection, to do the email exchange, and to close the connection. In the email exchange, there's the control message part and then the actual data part. And that is an SMTP message exchange among the client and servers. Let's try now to telnet to an actual mail server at port 25 and see what the server would send back to us. And then we could try to typing some of these comments out and see how the server responds. So let's go to the demo mode. Now let's try telnet to a mail server at port 25. Telnet, which mail server? Actually googled up Gmail's mail server. The name is this, SMTP, how appropriate, gmail.com, 425. There we go. IP address being 64 something something. And this is a message coming from the server, 220. All right, so SMTP, gmail.com there is identifying itself. And then ESMTP, okay, it's saying more. I'm not quite sure what this is, right? So E must be something and then SMTP. So this might be a special variation of SMTP, maybe the encrypted version, I'm guessing. So let's try typing up some of the comments. For example, hello. and coming from us, .edu.tw. How about that? Great, seems to be working. 250. So the server say, ooh, address service. That's really polite. All right. Then let's try the next comment we saw earlier, mail to, and let's have Gmail sending to Polly's email address. How about that? What is this? 530 5.7.0 must issue a start TLS comment first. So yeah, it does look like it's trying to establish an encrypted connection. So TLS, if you recall, is what? Transport layer security support. So I'm guessing this is probably the credential, the public key. So I'm supposed to send back the share secret key with the public key as the key to encrypt. But I don't know how to do that. So yeah, let me try it again then. Playing dumb here. poly@ntu.edu.tw. Let's see. No, it's not accepting it. So I have to, yeah, so maybe recipient from, yeah, Polly's Gmail address. How about that? No, it keeps bugging me saying, okay, let's do start TLS. So that's issue this comment, start TLS, and see, start TLS. Oh, cool, it's accepting. That's nice. Ready to start TLS. All right, so then I suppose I need to send back the, I'm already out. So it seems that the establishment process there also has a time limitation. Otherwise, yes, and hacker might be able to hijack something that you have done in the middle. Interesting. So, hey, I got kicked out. So Gmail is a secure email service. Email messages are encrypted. Nice. Good to know. And so that was a demo of trying to tell them to a mail server, actual mail server. You could also try this yourself, maybe from the workstation. Okay.
All right, so that's a demo. Okay, the next video is to tell you a little bit more about the messages formats, and that includes the messages for the comments as well as the email itself. Okay, so there are messages that the mail server send to each other, but to send comments. So hey guys, I'm sending an email over now, and then there will be also inside that message, there's going to be a body which contains the email, and those emails will also come in a certain format.
And just a few words about SMTP at the end. Once it sets up a TCP connection, the client there can use the connection to send multiple emails. So it runs just like the persistent connection we see in HTTP. SMTP requires text in ASCII code, very strict. And SMTP uses just a single dot in the last line, okay, to determine whether it's the end of the message. Now, if we compare SMTP to HTTP a bit more, they differ in multiple ways, but they are also similar in another way. So this is the first thing they're different. Yeah, the service sort of direction. HTTP is actually to pull objects down, but SMTP is to push objects out. Now, object here, I meant email. They are similar in this way. Comments, responses, all these messages are in ASCII text format. But HTTP and SMTP are also slightly different in this way. Each object is encapsulated in a response message. So HTTP server there sends one object at a time, one object per message. But SMTP can send multiple objects in one message. That message is just having multiple parts. So for emails, that comes with an attachment, like a big PDF file after, here is the attachment. If there's anything wrong, contact me. So email, the original text at the beginning, and then additional attachments. They can be sent as a multi-part message. So multiple objects in one message versus HTTP. One object, one message. Mail message format. So there's yet another protocol that defines how the email messages should look like. So this will be the data part of the SMTP protocol message exchange. If you recall in the example earlier, there's the opening phase, some control messages being sent, and then comes the actual data before closing. So the mail messages here we're talking about is the content being sent in the data phase. All right, so these messages are not control messages for SMTP. So they are not SMTP. The mail message format is actually defined in another RFC. It's another protocol. So in that protocol, it defines the mail message format. There are two parts only. The header containing a number of header lines, specifying who the receiver is, who the sender is, and what is the subject of the communication. In the body, very simple, just the content of the communication. So note again that I try to clarify. In SMTP, you see mail from. So this sounds like, following this command, you also tell who the sender is. Receive to, after the column, you give the recipient's email address. So it sounds a little bit like the to line in the header line and the from line in the header line, but they are actually completely different things. These go in the data part, while these go earlier, setting up a connection ready for data exchange.
Yeah, so some of you guys might be thinking that in the demo Poly Shield, I do receive from, but it should be receive to, right? So it could be because that the comment that I issued are not exactly correct. So Gmail server rejected my comments. Could be. All right, so now we're done with SMTP. The next topic is the mail access protocol. You've heard Sophia talked about it. You see in quiz 12 slides, IMAP and POPs. There's a variety of protocols. But let's hold on to play the video after we take a break. It's now 11:18. Let's take a break and resume 11:28. right, guys, it's 11:28. Let's resume the lectures. So the last video is about the mail access protocols. So you will hear about POP or POP3 and IMAP officially.
And then we'll switch gear just a little bit and talk about the last part of email application. So we've talked about the flow of sending an email all the way from Alice to Bob, right? So mail access protocol runs here. Okay, so it's this part of the entire flow. SMTP that we talked about earlier only covers email exchange to the receiver's mail server. In between the receiver's mail server and the actual receiver, it's this protocol that's controlling. So what it does is to allow the receiver to retrieve email from its local server. There are three very popular mail access protocol: POP3, Post Office Protocol, IMAP, Internet Mail Access Protocol, and HTTP. These two, you can see that they are more specifically defined for the purpose, allowing a receiver to retrieve email. The functionality is also similar. First, the receiver needs to authenticate itself, authorize itself, and then begin downloading emails. IMAP, being a slightly newer version, okay, it includes a number of other features, including, for example, we could store the email messages in a more structural way, for example, creating folders and putting certain emails in certain folders. Right. HTTP, however, is special. It's quite fashionable these days. Some of the mail service providers are asking us to use a web browser as the user agent. And then the email server there is essentially also a web server, so that it runs HTTP in the middle and treating each email as a web object. So fetching an email, fetching a web object. Okay, it's the same thing, except that the content is more specifically being emails. And let's take a closer look at how POP3 works. Okay, the exchanges between the client and the server. The notation is very similar to the exchange we saw earlier in SMTP. S being the server, client is C. So there's an authorization phase and then the actual transaction phase. So authorization phase you see here, the client comments very typically being declaring the username and declaring the password. So you see here in the authorization phase, server says, okay, I'm ready. Client says, I'm user Bob. So the username there is Bob. Password being hungry. All right. And server responses with either okay or negative error. It's even more simpler. All right. So okay here, okay here, okay here. Maybe with the phrase after that. And in transaction phase, this is where the emails are actually retrieved. So clients sometimes say this, list. So this is to ask the servers to tell back the list of emails there are. So this is more the index of the emails, and a lot of times just containing the file size and maybe the subject line. Right? It's only until the client begin issuing comment like this, RETR. So this is for retrieving messages. So RETR1 indicates that it's retrieving this email. So this is the index of the email, the size of the email, and there could be other information. Then the server sends back the actual content of the first email, and again ends with a period, and only one period in the whole sentence. Right? The client can actually delete an email that has already been read, or in case it's a spam. Right? So DELE, very intuitive, being the delete. Quit, also intuitive, being quitting the session. All right? So retrieve an email, server sends an email, client delete an email, retrieve another email, server sends another email, and client deletes yet another email. Q and then plus OK, server says goodbye. So that's an example of POP3 exchange.
All right, so that's the end of email, the second application. Now we talk about the third application. It's DNS. I don't know. Have you heard about DNS before? If you do, say yes on the chat. Okay. If not, then say no. DNS. It's called Domain Name Service. All right. So this is going to be our third application. Okay. I see many of you have heard about it. Just a no. Zhiyu says no. Okay. Yeah, I guess yes and no. And more say yes than no. Yeah, so this application is a little bit tricky. In fact, guys, it's actually arguable whether it's an application. Okay, this is I personally feel the most interesting protocol running on the application layer these days. Okay, so why don't we go ahead and start? The first video is exactly to tell you what it does. Okay, you'll be surprised.
Next is chapter 2.4 DNS, which stands for Domain Name System. And before we talk about the purpose of it, let's talk about identifying a person. If I tell you my social security number, my name, and my passport number, which one would you think would be easier to memorize? Well, social security number, 10 digits long. Well, the national ID of Taiwan is also about 10 digits long. You can correct me if I'm wrong. Name, Polly Huang. Passport number, don't even bring this up. Polly does not recall her passport number, as a matter of fact. So very obvious, isn't it? The name is so much easier. But that's just how human brain works. Name, form of ID, much easier. Number, form of IDs, harder, especially when it's a long sequence of numbers. Well, internet, to identify a machine on the internet, shows a similar obstacle. So hosts and routers, many of them have the IP addresses, right? But these IP addresses are even harder to memorize, maybe harder than the passports. And as you're working on the PAs, right, memorizing the IP address of the workstation, super hard. Even though you've already worked on it for a while, if I ask you to type it up, it's probably still challenging. So what we do here on the internet is to give some of the important machines also a name. For example, www.yahoo.com here is the web server of yahoo.com. So you could just type www.yahoo.com and it quickly leads you to Yahoo's website. Similarly, www.google.com, quickly we reach Google. So, hey, how does the web browser know? What is the IP address of the web browser given just www.yahoo.com? Well, that is the functionality of DNS, to identify the mapping between the IP address and the name. And let's talk about DNS more formally. So essentially, it's a database of these mappings. So lots of these IP address mapping entries. Nowadays, it's distributed, meaning there are multiple of these name servers. And there's a hierarchy actually connecting these name servers. Some of them sitting at the higher hierarchy and some of them sitting lower. What's a bit special about DNS here is if you hear me saying that, hey, a web service will need to query DNS system in order to find the mapping. So, hey, web service is already an application level service. HTTP is already the application layer protocol. So it seems that the application layer protocol, HTTP, there needs to work with DNS, which is also an application layer protocol, in order for it to operate correctly. So DNS, in fact, work with multiple of these application layer protocols, not just HTTP, all right? So name servers there would help all these application layer protocols in order to resolve names to the IP addresses. It's a very essential function. Some might argue that it's one of the core internet functions, which might sit underneath the application layer protocols instead. But now we put it in the application layer such that it's only running on the end hosts. If we need to update, improve the DNS servers, we don't need to actually go ahead into the core of the internet, all these routers, to change everything. So that makes changes a bit easier. Right? So there's a very special phrase that the internet designer would like to say, which is complexity at the network's edge. What it means that if you come up with something, some function that's very essential and it could go complex, then let's put it at the edges. Let's have it running on the hosts instead of running in the routers at the core of the internet. Okay. And a good side of doing this is so that we could evolve quickly and the performance bottlenecks can be removed quickly. Right.
All right, 2 key points here in that video. What is the purpose of DNS? It's to try to find the IP address. So IP address is what's the most important information allowing us to send data to a particular machine. So we need that machine's IP address. But we don't. I mean, it's hard to remember a series of numbers, So we use a name very often to represent the machine instead of the IP addresses. And in order to translate from the name to the corresponding IP address, we have the DNS, okay, Domain Name System Service. Now, guys, if you think about it, hey, this is a function that is, very necessary. Every time you click on the link to access a web object, or you send an email, right, to ntu.edu.tw, okay, or mail.ntu.edu.tw, or I just demo smtp.gmail.com. Yeah, each of these machines, we're actually referring to them by their names. Okay, so you can see DNS, this service is being used all the time for every web object request, for every email we send. Okay, the frequency we use this service is actually more than sending emails, more than web objects, actually all of those other applications combined. So this is a very important service, in fact. You might be more aware now. And how come we don't implement such an important service at the lower layer? Because, hey, for every request for any information, okay, from a server or from another machine, unless you know the IP address, we need it. Okay, so typically we do that in a lower layer because it's a very fundamental service. But actually, we implement it in the application layer. Okay, do you recall at the very end of the video why? Yeah, we put the complexity at the edge of the internet. There's a very good reason for that, because it's very hard to change the core of the internet. The core of the internet are what? The routers. They are very, very busy forwarding packets. Okay, so for complexity that are not necessary in the core, okay, if they are not necessarily in the lower layer, let's put it at the higher layer. That way it will be easier for us to change, okay, and evolve. Okay, complexity at the edge. That's one of the design principles architecting services on the internet. Now, with a good sense of what DNS is doing, let's find out DNS, domain name systems, the functions there are. It's not just to translate from the name to the IP address. There are actually a few more additional functions. So pay attention.
DNS services. There are multiple services actually DNS provides. First is what we've talked about, the most basic one, from the host name to IP address translation. It does three other forms of translation. First is the host aliasing. So what happened often on the internet is that some hosts came with host names, but the host names could be slightly longer, indicating where it is or which one of it, number 1, number 2, number 3. Okay, so those can still be slightly harder for users to memorize. So alias name here is often cute and short and very easy to memorize. So this is where the users know the services are, such as .google.com. All right, so from alias name, DNS allow the web browser to look up what is the canonical name of the server, and from the canonical name of the server, identify the IP address through one of these mappings from host name to IP addresses. So that's how host aliasing works. Second, mail server aliasing, right? So I mean, you must have one of these, right? Gmail accounts. If your friend is sending email to your Gmail account, your friend's mail server will need to know who's your mail server. So who's Gmail's mail server? This thing actually looks very general. It's in fact a domain name, not quite a host name. So what happened in DNS is there are also these entries saying for this domain, gmail.com. Okay, all the emails destined to this domain should send to this machine, smtp gmail.com. This we talked about when we were telnetting to an email server to demonstrate the message exchange there. smtp.gmail.com is the actual mail server for gmail.com. So there are also this entry here in DNS service. Okay, and this is called the mail server aliasing service. Last, okay, this one is a bit tricky, but it's growingly popular. It's called the low distribution service. What it does is this: for a host name, there could be multiple IPs that map to it. So IP1, and then the same host name, IP2, IP3, IP4, and so on and so forth. Okay, what happened here is that the DNS might actually rotate, returning different IP addresses each time a web browser or an email server looks up for an entry, okay, for the particular host name's IP address. So that way you kind of rotate using different physical machines every time, and therefore distribute the load of the service. Why not centralize DNS? You heard in the previous slides, there are multiple name servers and there's a certain hierarchy behind it. So why not just one? Well, it doesn't take long. At the beginning of the internet, there's indeed just one DNS server, but it doesn't take long that we realize when the machine is off, the entire DNS service is off. And everyone on the internet, unless you can memorize the IP addresses of all these servers, otherwise, there's not much you can do. Okay, it's off. Second, every application that needs to find mapping IP address given the name, traffic needs to go there. So very high volume. It gets really busy at times. And hey, those users that are around this particular server will have short delay, but they will always be part of the world far away from a particular machine. So delay not ideal. Some could suffer forever. And maintenance, this is a tricky issue, but it is indeed a problem. There are two perspectives looking at the maintenance issue. One is that the DNS server software is growing large. When it grows too large, if you want to make just a tiny little change, you need to what? Turn off the machine, update the code until you can put it back running, right? But all you want to do is just to make a small change. So one small change influences the entire internet. Not good. Second, it's also hard to do the maintenance, right? Because if you want to just do some testing, debugging, you have to take down the entire DNS as well. And when the software grows large, chances is higher that you need to do the testing longer, debugging longer. Not good either.
All right. So you see two key points from that last video. One is that DNS is not strictly doing just name to IP mapping. It does also what? Longer, complicated name to shorter, easy to memorize nickname mapping as well. It also does domain to domains mail server name mapping. So in order to send emails, a lot of times you query the DNS service to find the domain to the mail server's name. And then you query again from the mail server's name to the IP of the mail server. That way then you can start send emails. Okay, so in a way you use DNS service not just by querying once a lot of time. You might need to query a couple more times, eventually getting the IP address. Then you get the message sent to that destination. Okay, there's also load balancing. But you see, DNS, as Polly explained, it's a general service. So we're using it all the time. And you can imagine the servers, DNS servers are very, very busy taking queries from the world and frequently for every service we use, essentially. So having just one central DNS server for this service, it's not possible. Okay, so we have a distributed network of these DNS servers. Okay, so next video here explains what the components there are. So there are actually servers that are higher level, okay, managing the lower level server managing the further lower level servers. Okay, so there's a certain hierarchy maintaining these mappings. Okay, so let's check out the components, the various DNS servers.
Therefore, DNS is not a centralized system, but rather a distributed hierarchical system. And this is how the hierarchy looks like. At the top, the root DNS servers. Second level, the .com, .org, .edu DNS servers. The lowest level, or the authoritative server level, the yahoo.com, amazon.com, pbs.org, poly.edu, umass.edu. So what you're seeing here is, hey, .com further breaks up the namespace, and each of these servers at the bottom will serve a small range of the names there are on the internet, right? So distributing the load of the name IP lookup. Now, the process of looking up the IP address in a nutshell is this. Client now wants to get the IP address of, for example, www.amazon.com. What it does is first query the top server and try to find the second level server. Query the second level server, next try to find the authoritative name server, the last level. And then from the last level of DNS servers, finding the IP address for a particular host. And let's talk about each of these name servers a bit more. At the top level, the root name servers. It's connected by the local name server. Now allow me to explain. This local name server is not in the hierarchy. This local name server is actually very, very close to the client. Typically what happens is that a whole bunch of these end hosts sitting in an ISP will be sharing one. So ISP or institutional network will set up a local name server there for all the users in the domain to send the queries. And then this local name server then will relay the queries to all these servers in the hierarchy, right? So in a way, the local name server here is the client of the name to IP lookup service. So a local name server contacts the root server first, right? The root server then will contact the authoritative name server to find the mapping, get the mapping, and then return mapping to the local name server. Now, the trick part is this. When I say contact authoritative name server, it's not like directly going from the root to the authoritative name server. There's a certain way of rerouting the query until it reaches the authoritative name server. Authoritative name server is really the one containing the name and IP mapping. Okay, the top level knows the second level. Second level knows the authoritative servers. Only the authoritative name servers knows the exact mapping. And you see here, there are not many root servers. There are 13 logical root name servers, but each root name servers now have multiple physical sites. For example, here in Tokyo, there are 5 sites, 37 sites just for the Swedish root server, etc. So there are quite a few in America, but essentially very few of these root name servers. Next, the second and the third level DNS servers. At the second level, we have a bunch of these TLD servers, top-level domain servers. They're responsible each for a different top-level domains. So top-level country domains as well, UK, FR, CA, etc. So essentially, this is the last part of the host name there. Right? And each of these TLD server is maintained by some sort of organization of public interest. Some people call them NGO. So for example, Network Solutions maintain the servers for the .com TLD server and EduCops for the .edu TLD. At the third level, we have these authoritative DNS servers, right? So it maintains the IP host mappings. And it could be maintained by the organization itself or by a service provider if the organization is somewhat small and there are not many entries really. Local DNS server, this I tried to introduce earlier. It does not belong to the hierarchy, 3 levels. It's very special. Each ISP or institution network will set up one, and all the clients in the institution or in the ISP will configure themselves to send all the queries to this local DNS server, which is also called the default name server. So when a host makes a DNS query, query is always sent to the local DNS server. These DNS servers often carry these caches of recent translation. So whenever we get a host to IP address mapping to the local DNS server, of course, forward the answer back to the client. But in the meantime, the local DNS server also keep a copy of that, okay, for some time. And this is for the benefit that if the client is looking for the same name again, okay, same name IP mapping again, then it's conveniently already cached in the local DNS server, avoiding going all the way to the hierarchy. So nice. But be careful. These entries could sometimes go out of date. So while these entries are cached locally on the local DNS server, well, the entry might have been changed in the authoritative DNS servers. Okay, although very rare, but there's a chance. So these local DNS servers, if you think about it, it works more like a proxy server. Okay, it's not exactly client, it's not exactly server. It's something in the middle, helping relaying the queries, relaying the answers. Helping forward queries into the hierarchy if there's no hit here at the cache.
All right, so you see, the mapping entries are really stored at these authoritative DNS servers. Okay, So think of these are like, people really in charge of doing the translation. Okay. But there are so many of these because each organization needs to maintain their own server, the servers within the domain, and the name and the IP address mapping. Okay. And there are so many of these organizations. So in order for a client to ask for a mapping, right, the client needs to know which organization I asked first, and I need to know how to reach, the person in charge for each of these organizations. That's too complicated. Okay, too much information for the client to remember. So there's a hierarchy. So for a group of these organizations, there's a contact window. Okay, and for a group of contact windows, there's an even higher level contact window. So the client can just reach the root contact window, and the root contact window can just look at the last part of the host name and decide who's the next level contact window. And the next level can look at the last two parts of the host name and find out who's the real person in charge, who's the real authoritative DNS server in charge. Okay, so it is a database that is distributed, managed. And so us as clients, users, we ask the root. Root would direct us to TLS, the top level server. Top level server would then direct us to the authoritative DNS server. So that's the idea. The local DNS server is more like a web proxy to improve the performance, but it is so important because DNS is used so frequently. It's a must-have. So all of us will need to configure our computers to a local DNS server. Otherwise, it will be hard to resolve the name to an IP address. Right. The last video is to illustrate exactly what I just talked about. If I have a query to get the mapping from host name to IP address, how exactly this query is redirected through all of these DNS servers? Okay, first to the local DNS server, and then going down the hierarchy to find the authoritative DNS servers. And pay attention, there are two ways of doing it.
So far, we've learned that there's a hierarchy in the DNS servers. There's the top, second, and the third level. And we also know that there's a proxy server there, always working on behalf of the client, sending the DNS queries. So let's try to explain further from the local server here, how the query is forwarded, okay, and eventually receiving a reply. And let's do that through an example. Okay, there's going to be a host trying to reach Gaia.cs, but before messages can go out, CIS poly here needs to find the IP address of Gaia.cs over there. And we're going to illustrate this form of query forwarding. It's called the iterated querying. All right. So what the local DNS server does is to contact the server in the hierarchy, and the server will reply with something like this: name of the server to contact. Okay, someone whom I know a little bit better, but I don't have it. So messages looks like this. Root server might say, hey, I don't know about Gaia.cs.umass.edu in particular, but you may ask, hey, the top level domain server for .edu. Okay, someone knows slightly better than I do. Okay, but I do know someone who knows better. Right? So that's the general idea. And so the process goes: client here issuing query. Local DNS server now forwards the query first to the root. Root returns the IP address of the .edu TLD server. Therefore, the local DNS server could re-forward the query to .edu TLD DNS. Top DLD DNS does not know the IP just yet, but top level domain DNS does know the IP address of the authoritative DNS server, so that will be sent back. And the local DNS server sends the query the third time, okay, to finally the authoritative DNS server. And finally, the IP address for Gaia.cs comes back to the local DNS server. Local DNS server forward that back to the requesting client and be happy about it. Recursive query is the second form of doing the querying. So local DNS server here will forward only to the root, okay, and not contacting DLD, not contacting the authoritative DNS server. And it will be the root's job to find out what the mapping is. And root doesn't really know the mapping of Gaia.cs.umass.edu. So he forwards the query to TLD, TLD forwards to authoritative DNS server, and finally the IP address traverse back. And root DNS server here sends back to the local DNS server. Right? Can you see an issue with this? Yeah, so this way of querying puts burden on named servers that's high up in the hierarchy. There's going to be a lot of query comes to the root, and there's going to be a lot of queries coming from the root to the TLD, although the load on the authoritative DNS server remains the same, right? So heavy load at the upper level of hierarchies, not good. Keep in mind, there are only some tens of root DNS servers, physical root DNS servers. If everyone is sending the queries always to the root, we could quickly bring down all these root DNS servers. And that's not really a viable solution. Therefore, recursive query is an option that we try to disable at the local DNS server.
All right, so that's DNS and how it works. Okay, you can see the architecture is very extensive, much more elaborative than the email's server architecture, and email itself is already more elaborative than the HTTP's very simple client-server architecture. All right, that takes us to quiz 13. Okay, so let me use the whiteboard more directly here. Okay, so this is one of those open-ended quiz. Okay. I don't know about you, Polly likes to challenge herself and ask all sorts of questions, okay, making sure that she's sure what she's doing. Okay, so I recall when I was a college student, I asked this, hey, it's really time to get real. Okay, staying in school, things seems to be a little bit dreamy, doesn't seem to be real. Okay, so I don't know if you have thought about this. Okay, so Polly had many times tried to get real. Okay, and I would decide to do all kinds of things. So hypothetically, in quiz 13, you ask, it's time to get real. You decide that it's enough college education for you. Okay, so this is a little bit extreme. Okay, hypothetically, and you thought pet book is totally better than Facebook. Okay, it's a social network app for pet animal lovers. For example, using the pet's picture as the profile picture. And this is gonna go bigger than Facebook. Hey, why not? Each of us, we oftentimes have multiple number of pets, right? Each of us will have multiple of these pages on Petbook. Okay, the potential of it being larger than Facebook is so much higher. Okay, and so see, Polly made up a Petbook banger like this. Okay, and this is Honey, okay, Polly's pet. Okay, being also your being also your own CTO, in addition to being the CEO, CFO, and COO. So this is a one-person startup. Okay, thinking of it this way. Try to structure the Petbook server network and direct the pet page queries so that the server load is balanced and the delay is low. Okay, think DNS. It's a distributed database. I can tell you, Facebook is also a distributed database. Okay, it's a database storing information about you, the status you've posted in the past. Okay, everyone's status posted in the past. So it's a distributed database. All right, oopsie. Would you prefer modeling your service, okay, the server architecture, okay, that distributed database, and how the user sends query, okay, after A, the DNS, or the B, SMTP, or C, HTTP's architecture? Okay, hey, DNS, HTTP, and SMTP. Let's try to review the architectures of these three services. The simplest one is what? HTTP. Okay, and you see, straightforward, a client and a server, isn't it? Second, SMTP. A client sending email first to the local mail server, and the local mail server will send to the receiving mail server that is local to the receiver. Okay, so yeah. And DNS. Client sends query for name to IP address mapping first to the local DNS server. And the local DNS server, depending on the query model, iterated or recursive, it could be going like this. It could also be going like this and back. All right. Now, let's abstract these three different architectures this way. Okay, thinking the client side somehow between HTTP and SMTP is expanded. Right, the client side of HTTP and SMTP from HTTP to SMTP is expanded. Similarly, observe this. The server side of SMTP and the server side of DNS, okay, from one to another, the architecture is also expanded. So, talk about all these in general. Okay, we have three different architectures. On the left, very simple, straightforward. In the middle, expanded the client side. Towards the right, we expanded further the server side. Okay. And we know on the left, it's HTTP, that is A. In the middle, that is SMTP, that's B. On the right, that's DNS, that's C. And I hope it's clear the question is what the question is asking here. Okay, would you model your whole network to support Petbook over A, B, or C architecture? Please try to justify why you choose one architecture over another. All right. Let's move to the Discord space. There is a channel, W5 Quiz 13. Okay, we don't have much time. We have only 4 minutes. Okay, so you guys get your teammates. Okay, talk about it. And in case the time is not sufficient to get a answer that everyone agrees, it's okay. Consider this also a semi take-home quiz. Okay, but I think some of you might have a good idea. So you guys are given 4 minutes time. Okay, it's 12:04 now. Let's see what you guys can come up with at 12:10. Yeah, so we have Nicholas saying DNS. Yeah, DNS architecture is well elaborated to handle heavy load. I agree, totally agree, because Petbook is going to be huge, right? Anthony here is also saying, and with a little bit more analysis, HTTP model, it's not going to be desirable, isn't it? SMTP is better, indeed, with the proxy there, okay, helping the clients, okay. But DNS, because of the multiple layer architecture, okay, you get to balance the load a little bit better. Petbook is the future, yes. So very well role played, Jeremy. We'll need scalable servers. Yeah, guys, you got it. Yeah, so the reason that these different applications apply different architectures is because exactly the kind of load they need to address. And for extensive loads like what DNS is handling, you do need hierarchies. That's why big companies all come in levels of hierarchies. NTU also has levels of hierarchies. Okay. Very good. Yeah. Good. So that should teach you guys the architectures, the communication model you need to decide for the applications you want to design ahead. Okay. Good. So guys, with that said, it's time for the lecture this week. There's one more lecture next Wednesday. I'm gonna finish talking about the rest of DNS and cover P2P systems. Okay. From my experience, P2P is the most interesting chapter in chapter 2. Okay, to all of you. So do attend. Some of the exam questions might ask about P2P. Okay, so I see you again next Wednesday, and I say goodbye. Before I really say goodbye, let me just say that I'm gonna let the stream run for a couple minutes, and then I'm gonna close the stream, and then you would try to join the Google Meet session here. What I'm showing on the screen towards right, to test your camera and maybe also your microphone. All right, so it's now 12:12. I'm gonna close the stream at about 12:13 to 14, and after that, feel free to join the Google Meet session to check on your camera and internet connectivity. Okay, good. Bye. Okay. Jianbao, if I let you in, you're gonna show on the stream and everyone will see you. Okay. Okay, bye. Okay, it's 12:13. If I were an investor, I would like Petbook to use SMTP. Interesting, Justin. Okay, you were saying that maybe at the beginning you just use the SMTP's architecture. When it grows, then you switch to DNS maybe. Very good. Incremental thinking. Yeah. All right. So bye. Okay, let me close the stream.